everyone, my name is Rayhana Mejiasan. So before we formally start in our topic, which is third law of thermodynamics, we must know first what is thermodynamics. So what is thermodynamics? Thermodynamics, from the word itself, thermo means heat and dynamics means power. So that means that it is a relation between heat and motion. So, before we formally start, we must know first what is thermodynamical system. System, this is a group or collection of molecules which are related to each other. They have some similar quantities. So, what are those quantities? Those are known as thermodynamical parameters. System is a group of particles which is placed together. Thermodynamics can be classified into two parts, the open system and closed system. So say for example, the bottle in water. This water is air particles because it is different air particles around it. And it is closed system since it is enclosed in the container and no connection outside. And if it has no connection outside, then it is open system.
The third law of thermodynamics. The difference between the first law of thermodynamics, second law of thermodynamics, and the third law of thermodynamics. The first law of thermodynamics states that energy cannot be created or destroyed. The total quantity of energy in the universe stays the same. The second law of thermodynamics is about the quality of energy. It states that as energy is transferred or transformed, more and more of it waste. The second law also states that there is a natural tendency of any isolated system to degenerate into a more destroyed state. And the third law of thermodynamics is concerned with the limiting behavior of a system. As the temperature approaches absolute zero, most thermodynamics calculations use only entropy differences, so the 0 point of the entropy scale is often not important. The third law states the entropy of a perfect crystal is zero when the temperature of the crystal is equal to absolute zero. The third law of thermodynamics. The difference between the first law of thermodynamics, second law of thermodynamics, and the third law of thermodynamics. The first law of thermodynamics states that energy cannot be created or destroyed. The total quantity of energy in the universe stays the same. The second law of thermodynamics is about the quality of energy. It states that as energy is transferred or transformed, more and more of it waste. The second law also states that there is a natural tendency of any isolated system to degenerate into a more destroyed state. And the third law of thermodynamics is concerned with the limiting behavior of a system. As the temperature approaches absolute zero, most thermodynamics calculations use only entropy differences, so the 0 point of the entropy scale is often not important. The third law states the entropy of a perfect crystal is zero when the temperature of the crystal is equal to absolute zero. Absolute zero, temperature at which a thermodynamic system has the lowest energy. It corresponds to negative 273.15 Celsius on the Celsius temperature scale and to negative 459.67 Fahrenheit on the Fahrenheit temperature scale.
Good day everyone, I am Maybelline Omar and I will show you an example of how to calculate an absolute entropy. But before that, let us summarize what is absolute entropy and third law of thermodynamics. An absolute entropy represents the entropy change of a substance taken from absolute zero to a given temperature, or at absolute zero, every substance will be a solid given things like hydrogen or helium. And one way of summarizing the third law of thermodynamics is by saying that the entropy of any crystalline substance at absolute zero will be equal to zero.
This is a necessary consequence of Boltzmann equation. S equals K sub B times ln of W, where S is the entropy, K sub B is the Boltzmann constant, which is the 1.38 times 10 to the power of negative 23, ln is natural logarithm, and W is the number of microstates. If there is no kinetic energy, nothing is moving, so there is only one possible microstate that the particles can inhabit. With the value for W equal to 1, the natural log of 1 is equal to 0. So, at absolute zero, the entropy of any substance must also be zero. However, absolute zero can never truly reach, which is communicated in praising the third law, which states that it is impossible to lower the temperature of any system to absolute zero in a finite number of steps. Now, let us proceed to the example. An oxygen molecule is absorbed on the small patch of the surface of a catalyst. It's known that the molecule is absorbed on 1 to 36 possible sites for absorption. So, basically, we'll be using the Boltzmann equation, and that is S is equal to K sub B ln of W. In this case, W is 36 possible sites for absorption. In this particular case, they tell us that it's one of 36 possible sites, so we know that is W. W is 36, the number of possible sites. So W is 36, the number of possible sites. So S is equals to the Boltzmann constant, which is 1.38 times 10 to the power of negative 23 joules per Kelvin times ln of 36. So multiply this one to ln 36 and it gives us S is equal to 4.95 times 10 to the power of negative 23 joules per Kelvin. It gives us all the entropy, and you might notice that it is a really small number. But note, this is the entropy for one molecule. So if you have a lot of molecules, then you might have a lot of entropy.
Hi, my name is Akria Datumanong. Today, I will discuss the third law of thermodynamics. The entropy of a pure crystalline substance is zero at absolute zero temperature. Published in Nature Communication, a team of researchers based at the London Centre for Nanotechnology, in collaboration with scientists from Oxford and Cambridge, found that, against expectations, the third law of thermodynamics will be restored in thin film of magnetic material spin ice. On Earth, it seems as if also anything can be cooled down. But researchers established an object eventually reaches a point where it can't get any colder. This temperature is referred to as absolute zero and is equivalent to minus 273 degrees centigrade. At this degree temperature, it is believed that the entropy of a substance or object could also be at zero. This idea is called the third law of thermodynamics. Spin ice has proven to be an exception to this law. In spin ice, the atomic magnetic moment remains random as absolute zero is achieved.
This allows the spin to hold properties that most things don't, such as magnetic monopoles.
In order to conduct their research, the scientists create spin ice that was only a few nanometers thick. They found that when the temperature was about half a degree above absolute zero, the entropy of the spin ice disappeared completely, proving the third law of thermodynamics was restored. The X-ray observation showed the substrate that held the film applied some strain, which is what caused entropy to be lost. This result shows that we can use strain to districtly alter and control the spin ice state, says Dr. Laura Bovo of the UCL London Centre for Nanotechnology and leading author of the team's paper. Said in the news release, it opens up new possibilities for the control and manipulation for magneticity and magnetic monopoles in spin ice.
Hello everyone, I am Jessica Linawagan and I will explain what is the purpose of the third law of thermodynamics and what is the importance of it. So, the third law of thermodynamics has two important consequences. It defines the sign of the entropy of any substance at temperature above absolute zero as positive, and it provides a fixed reference point that allows us to measure the absolute entropy of any substance at any temperatures.